Okay. Let's start. Let's close here. So the idea today is to finish the exercise that we started last time. Okay. So that we will be able to dedicate the remaining time to the last topic of the course, which is the reduced order modeling technique. Let's see if we, all right, so basically last time we started off from the assembly of the matrix of mass of the overall body, then we moved to the stiffness matrix, first the structural stiffness matrix, and eventually to the overall stiffness matrix of the body. And we also started the example of a 2D beam element with the objective of deriving the mass and the structural matrix of the element. In so doing, we defined a series of topics to, let's say, specify, in the case of a 2D analysis, the findings that we generally derived for the 3D case. Okay? And so we basically arrived at the point of, again, describing the shape functions of the element with reference to the C1 and C2 matrices. And then eventually, we were able to define the N matrix, which links the vector of the nodal coordinates of the element expressed with respect to the body frame to the position of a point of the element expressed again with respect to the body frame. Okay, so this is where we left. Now, today's topic is to eventually move forward from here. And so basically what we will do is to calculate the mass matrix of the element, okay? Of the element, of course, J of the body height. Okay, so again, we start from the typical expression of the position of a point that we know as this form for the element J, where, of course, the matrix A is the typical matrix of rotation into 2D case. Okay, so something that we should be well aware of. And this is, of course, the rotation, the rigid rotation theta I, which, of course, only has the I superscript because it's referred to the overall body I. And then from here, we move to the definition of the position of the velocity of the point P within the element J. And we basically perform a derivative with respect to time, taking into account the position that we just, let's say, expressed. Let me just, of course, here we have a, sorry, forgot a point, of course. And then we can further specify this as Ri dot plus AI theta times theta dot I times N Ij QE, right, QE I plus AI N ij and QE I dot. Let me, in fact, insert here something that we missed. All right. Of course, we miss a point here, so let's put it like this. Okay, we missed this point here, of course, because we know that this is dependent on time because it depends on theta. All right, so it has to be present when we derive with respect to time, where, of course, the derivative with respect to theta of the rotation matrix is straightforward, no? So it's minus the sinus of theta I minus cosinus of theta I, cosinus of theta I minus sinus of theta I. Okay, of course, it's just the derivation of what we have on top. With this in mind, yeah. Because most probably I mistook it, because this is, of course, like this. Yeah, correct. Yeah, of course, this is the vector of the nodal coordinates, which refers to overall body, okay, not just to the element J. Okay. From here, we can therefore, or let's say, write in a more compact way the velocity of a point P as the following quantity. Let me just okay. And so we have here Q. Let me check. Let's write it like this. N ij QE I, and then we have AI N ij applied over the vector of Ri theta, the differential with respect to time. And then we have theta I, again, dotted, and then we have QE I, like so. Okay? With this in mind, as we have already done, we have the Kij is 1 over 2 of the integral with respect to the volume Vij of rho ij p dot ij transpose apply over p ij dot over the v. And this, in turn, can be written as we have seen. Let me just save some space. Becomes 1 over 2 of Qi E transposed dot applied over M ij applied over Qi dot. Okay? E. Where, therefore, Mij in the 2D case becomes the integral over Vij of rho ij of, let's say, this matrix here, basically, applied over its transpose. So we have the identity matrix here. Then we have A theta I Here, if you want, you can write it as Rij, okay? Because basically this one is Rij, okay? So this here is basically this one, okay? So we can write it like this. And then we have, of course, A, I, Nij. Then we have, of course, Rij transposed applied over R over bar Ij. And then we have Rij applied over what we have already introduced to be this matrix I tilde, if you remember, and A Ij. Okay, where this, if you remember, for those of you who don't remember, this is something of this form. It's basically kind of an anti-symmetric matrix, not really, which is done like so. 0, minus 1, 1, and 0. Okay, it's just for us to define. And this is basically the result of what you get when you apply A derived with respect to theta over itself, okay? So when you do basically, when you apply this one over this one, okay? So A theta over A. All right. And then, of course, we have, let's say, the last term on the bottom, which is Nij transpose over Nij. Okay? And all the rest, of course, is symmetric in the B. Okay? So this is what we have to calculate, if you want. And these are the submatrices. And what we want to find out today is that basically, given the inertia shape integrals that we have found, we can express all of these matrices with respect to those. Again, in the idea of being able to calculate once and for all a certain number of quantities which stay constant during the simulation, so to ease out the calculation and the updating process of the matrix of mass during the simulation as the time goes, okay? All right, so what I'm saying is that we can cast, so having in mind again, we have one MRRIJ is basically from the, let's say, the calculation that we have carried out so far, is just the integral of the density over multiplied by the, let's say, the identity matrix. And this is, of course, Mij 0, 0, Mij. But this is constant, of course. And this, of course, is the mass of the element J. Okay, so this is the mass of the element J. Then let's go straight forward to MFF ij, because this is kind of easy, let's say, to calculate, and then the result is useful for the other submatrices to calculate. Okay, so again, from the resulting calculation that we have carried out, this rho ij and ij transpose are applied over nij in the V. And this, bringing out again of the integral sign all of the quantities which are not space dependent, becomes C1 transpose ij applied over the integral over Vij of the density applied over psi ij, which is the shape functions of the element that we have indicated at the very beginning of the exercise, if you remember, in the V. All of this being multiplied times C1 ij. Okay, where here, for the sake of clarity, there should have been, here, let's say in the middle, we should have had something of the sort of C2 ij transposed applied over C2 ij, okay? But this, I didn't put it inside because this is exactly the identity matrix, okay? Here, between the two, let's say, shape function, I should have had C2 transpose applied over C2, okay? By the definition of the matrix N, if you remember. Now, if you perform C2ij over C2ij, you get the identity matrix, okay? Because it's a rotation matrix. So, as it should be, it is orthonormal, okay? Orthogonal. And so, you have the identity matrix. If you remember, now, we had defined the following quantity, S, C, Psi, F, F, over bar, Ij. This is among the quantities that we have defined prior carrying out the exercise. This was a 6 times 6 matrix, which we define as C1 Ij transposed, which is a 6 times 6 matrix, over the integral Vij of rho Ij of Psi Ij transpose apply over Psi Ij in the V, and then multiply times Psi1 Ij. Well, this is exactly our matrix. You see? And therefore, our MFF Ij is exactly this first inertia shape integral, if you want, that we have defined for the 2D case. Okay, so S, F, Psi, Psi, F, F. Okay. All right. Now, so this is, let's say, if you want, so this is the second result that we have defined. Well, if you want, this is the first, but okay, it's kind of trivial. Okay. So here, with the definition of this matrix, we have already, this inertia shape integral, we have already basically calculated once and for all this submatrix. Let's move on to the next one, which is MR theta Ij. Again, the integral over Vij of rho Ij A theta I R over bar ij in the V. Of course, again, all of this information comes from the calculation that we have done so far. And this can be rewritten as A theta I, the integral over Vij of the density. Let's write this as Nij applied over Qei in the V. Okay, where again, this is exactly this. And from here, you can rewrite A theta I applied over. Let's again unpack the matrix N. So we have C2 Ij, and then we have the integral over the volume of the element of the density, the shape matrix C, the V, we close the round bracket, then we have C1, and all of this multiplied times QE I, okay? Now, again, if you go and check, we had already estimated the quantity between square brackets. So that we can call it A theta I that we have already estimated. This was S over bar Ij C applied over QE I. Okay, where again, all of this quantity that we have already estimated, we defined as Sij. Okay? So again, estimated once and for all. And so this is basically, if you want, the third noteworthy result that we have. Move on to the fourth. Which we have MRFij, and this is the integral over Bij of the density, again, of A, I, applied over Nij. Again, here, the trick is to unpack N, and unpacking N, and bringing out from the integral sign everything that we can, so everything that does not depend on space coordinates. We have the density of Vij of rho ij C ij in the V C1 ij, everything closed. As you can see, this is what we have just used. So this is A I times S over bar Ij C. Okay, so again, you see, once we have defined this second inertial shape integral, we can use it again. So this is this. And this is the third, actually the fourth noteworthy result. Okay. Let's move to the fifth. where we have M theta theta I Vij of rho Ij R Ij transposed apply over R Ij. So again, here you can see that what is the dimension of this matrix, in fact. I denote it as a matrix, but it's a scalar. Does it make sense? Yes. How many rigid rotation variables do we have? One, it's theta, so that's why it's a 1 times 1. So if you want, you can either write it like this, or you can write it like this, and then is a 1. You know? It's a matrix of order 1. And so we can again write it as follows. Again, here we have made use of the fact that this is basically Nij times Qi. Okay. Now this can be written as such. QEI transposed applied over M F F Ij times QEI. Okay, because you see that this quantity here is exactly M F F Ij. We have already calculated it. That's why I anticipated it at the second point, because we can, use it here. All right. And again, here you have, if you want to check the dimension, here you have 1 times 6. This is 1 times 1, and this is 6 times 1. Sorry, this is, no, sorry, this is a 6 times 6. This is a 6 times 1. Okay. All right. Last, you have the 6th coordinate. Mij theta f, the inter over Vij of rho Ij R Ij transposed, where here we have again the matrix that we have just defined. So I tilde actually, and Ij in the V. Again, remember that this is the matrix 0, 1, minus 1, 0. And so this can be written as Qi I transposed applied over what we have defined as S C C F F Ij, where again S C C F F Ij so sorry, let's actually use here a tilde, because it's different from before. This is C1 ij transposed, Dij rho ij. Here we have psi ij transposed. The difference from the previous definitions is that here now we have this I tilde. That's why the tilde. Ij, the V. And then everything multiplied times C1 Ij. Okay? Yeah, again, here we have that we have exploited the fact that Rij is Nij times QEI. Okay, so that's why you have this QEI here expressed. All right. So this basically closes the calculation of the mass matrix, because eventually, you see, it means that if we have these three quantities, so this S, psi, Cij tilde calculated, and then we have, so then, oops, if you want just to use the same notation here, we have this. Okay, so this is one of the sum matrices that we have to calculate. Then here we have MFF, which resorts to basically this S over bar Ij, see this matrix here. And then we have this S psi Ij, okay? So we basically have, in this case, we only have three inertia shape integrals. We have this one here, S psi psi-f over bar, S psi over bar Ij, and then we have S psi psi-ff over tilde Ij. So with these three quantities estimated once and for all, we basically have the matrix only, let's say, dependent on the quantities which we know already, that we want to find actually. So the estimation of the mass matrix is super fast. So basically, this closes the, let's say, the calculation of the mass matrix. I'm not sure if next time we're gonna perform also the calculation of the stiffness matrix. The idea is to basically, let's say, be able to close the course on Friday, because next week we're gonna have only 3 hours left, because I think the courses are supposed to stop on Thursday first. So Friday, we don't have a lecture anymore. So we only have 3 hours left. The idea is to employ the next 4 hours, basically trying to show you what ROM's techniques are about, and make a couple of examples with the Gaian iron and Craig-Bankton techniques. And also, let's say, reserve half an hour at least for the presentation of some possible thesis topics. Okay, so my idea is to eventually close the course basically on Friday. If we are not able to, on Friday, at maximum on Monday next week. Okay, this is it.